When we look up from an open ground, the lights of the sky move with a mathematical precision that suggests a much larger system in motion. There is a specific logic to what we see. Some objects twinkle because they are stars, generating their own heat and light from trillions of miles away. Others shine with a steady glow. These are the planets, which emit no light of their own and simply reflect the stars they orbit. Our solar system is a single neighborhood within this sprawling collection of stars, the Milky Way galaxy, also known in India as Mandakini. But within this ordered system, there are specific moments where the rules seem to fail. We see planets that appear to spin backward, and years that refuse to fit into a standard 365-day count. Becoming a Balvaidnyanik, a young scientist, requires looking past the familiar patterns to investigate these specific anomalies. Most planets in our solar system spin from west to east. This shared rotation is why, from our perspective on Earth, the Sun always rises in the east. Venus is the exception. It rotates in the opposite direction, spinning from east to west. This reversed rotation changes the very nature of the horizon. From the surface of Venus, an observer would watch the Sun rise in the west and set in the east. These differences define the geography of our solar system. Beyond the rocky inner planets and the debris of the asteroid belt sits Jupiter, the first of the gas giants, a world so large it could hold over 1,300 Earths inside its stormy atmosphere. Even within a single family of planets, the most basic expectations of scale and direction can be completely inverted. We also share our space with comets, visitors made of ice, dust, and gas. As they approach the Sun, their frozen material evaporates, creating the long, glowing tails that make them visible from Earth. This is Halley's comet during its 1986 approach. It travels on a long, elliptical orbit, bringing it back into view at regular, predictable intervals. Historically, astronomers recorded sightings of this specific comet in 1759, 1835, 1911, and 1987. Plotting these dates reveals a consistent 76-year interval. By applying that same mathematical delta to its last appearance, we can predict that the comet will return to our skies in the year 2061. These visits show that even the most fleeting events in the sky follow a strict, calculable rhythm. The Earth's own timing is equally precise, though it doesn't align perfectly with our human calendars. We experience two distinct motions: rotation, which creates day and night, and revolution, which defines our year. While a calendar year is counted as 365 days, a full revolution around the Sun actually takes 365 days and 6 hours. Over 4 years, those extra 6-hour quarters accumulate. They eventually form one full 24-hour day that our standard calendar hasn't accounted for. We resolve this discrepancy with the leap year. Adding a 29th day to February every 4 years prevents our calendar from slowly drifting away from the actual solar seasons. Our systems for tracking time only work because we adjust for the fact that the universe does not operate in whole, even numbers. The Moon, our only natural satellite, follows its own cycle. Its rocky surface has no atmosphere, and its changing appearance, from the waxing phases of Shukla Ekadashi to the waning of Krishna Ekadashi, is determined entirely by its position relative to the Sun. Occasionally, the Sun, Moon, and Earth align with such precision that the Moon's shadow falls directly onto our planet. We call this a solar eclipse. During a total eclipse, the Moon momentarily blocks the Sun's light, turning day into night, and allowing us to see the glowing solar corona that is usually hidden by glare. Because the Sun's rays are powerful enough to cause permanent eye damage, you must use specialized protective filters to observe an eclipse. Viewing the Sun directly without these glasses is dangerous. These alignments are the most visible evidence of the solar system's mechanical regularity. From the backward spin of Venus to the timing of a leap year, the phenomena we observe in the sky are expressions of deeper physical laws. Scientific discovery often begins by investigating the anomalies, the specific moments where the universe refuses to follow the usual script. This process of rigorous observation and calculation is the legacy of Indian scientific leaders like Homi J. Bhabha, who used these principles to master the complexities of the physical world. Competitive exams often focus on these specific exceptions. If you can identify the 76-year interval between the historical sightings of Halley's comet, you can calculate its next return yourself. The solar system is a massive system of data waiting to be interpreted. Keep observing, keep calculating, and prepare for the next mission.